Okay, because a lot of people are doing this last minute, what I'm going to do is, without much explanation, I am going to just walk through a setup of pretty much assignment one. We've already gone through this in steps. I'm just going to go through it in one fell swoop, quickly, without much explanation. No, this is an entirely new simulation file. Nothing in here at all. Literally nothing. I just made it. The only thing that happened before this was I literally opened it and cleared the console. One quick note, this block doesn't need to be this wide. I'm making it this wide because hypothetically, this will be sort of similar to assignment 2 when we do three-dimensional wing analysis. So we're going to make this kind of large, even though only the size of this two-dimensional side, this one face on the side is going to matter for the 2D sim. And one thing I didn't tell you is when you're making scenes, you can just make an empty scene which has no displayers in it and build your own displayers as you go, which I'm doing here because I only want to display very specifically that subtract surface that we just made, or this subtract block that we just made. I accidentally clicked and dragged. Oh, right. Okay. Operations. That shouldn't. I accidentally made the domain before I told it that it was a two-dimensional thing. We're gonna try that again. Sorry, I turned the air domain into a region. Where I told it that we were dealing with. Oh, I also did it before I created badge for two. Now, under regions, we should only have some of these surfaces. Nope. We still appear to have pretty much all of them. Let me try making this again. Oh, yeah. So notice how this little red dot showed up? Um, that tells us that it has been badged for 2D meshing. We make a new region again. We see that there are less inlets, outlets, etc. What we want. So I will explain this really quickly here. So what I'm doing is calculating the velocity based on Reynolds number. So Reynolds number is equal to rho VL over mu, which is dynamic viscosity. So I'm having it compute. Actually, here, tell you what. We're going to do a couple of things here. We're going to make a couple of new parameters so we can vary this more if we'd like. Ref pressure, velocity, temperature. What else are we gonna need? We're gonna compute kinematic viscosity. Or dynamic viscosity, but I'm gonna make a parameter for it anyways. Pressure. 5. Note that technically, dynamic viscosity for air changes with temperature, but over reasonable temperature variations, it's not going to change much. Set this to our reference pressure. All pressures will be measured relative to that. Initial conditions, 0 gauge pressure. We will set it to our temperature. I need to actually, it's a good idea to avoid using things that could be considered keywords. So, I'm going to tell this is instead of just temperature, because that could be a keyword. We're going to make it inlet temperature, and we're going to make this inlet velocity. Both of those could very well be keywords. Mu. And then I'm pretty sure what it is going to do for air, because we told it it's an ideal gas, is... Oh, no, it's just a constant value. Okay, we're going to use our free stream mu. Or we could have it compute based on Sutherland's equation, but we're not going to do that. We're just going to leave it as a constant. But I am going to change this to what it had as the default value, which is 1.855 instead of 1.81. Pretty close, but slightly different. But as far as the velocity, which is an important one, we are going to take our Reynolds number. Reynolds number is equal to rho times v times L divided by mu. So rearranging that, we have v equals Reynolds number divided by rho divided by L, and then times mu. Calculate rho. We take our reference pressure, reference static pressure, and we are going to divide it by, so this is the ideal gas cell. So P equals rho RT. So P over RT is equal to rho. For air, R is 287. Temperature is whatever that is. We can close that off. So that is Reynolds number divided by rho times L is going to be and this is going to be dimensional. So, click OK. Oh, did I mess up here somewhere? Oh, I did mess up back up here when I was setting the initial condition. Doesn't like that I left it there. There we go. That's better. So should here. Look at this. We can, I think, see what value this is going to give us. So if we tell it 1.855 e negative 5, tell it 300 Kelvin, tell it 101.325 pascals. We're going to tell it from 100,000 to 1 million. It's just going to be a linear slope from somewhat less than 1 meter per second up till 7.5. So this is a pretty big wing. I believe that. We could also wanted to tag an extra 0 onto a couple of these. So if we wanted to get to a Reynolds number of 100 million, we'd need about twice the speed of sound. 10 million would be 75 meters per second, about 20% of the speed of sound. Makes sense, more or less. It's a relatively big wing. 2 meters chord is actually pretty large. So we are computing all of those. Let's make sure our boundary conditions are actually using them. So instead of, I accidentally collapsed that. Instead of just having static values, we will update these to use our parameters that we made. Those are fine. Those are adiabatic walls. Really, that's the only thing we need to update. These say 0. Oh, wait. Actually, nope. I lied. We do need to change all 3 of these so they have the right inflow temperature. Physics values, static temperature. Update this. So it says... Okay. There we go. Now we should be okay. Automated 2D. One. 1 meter. So 100 is usually fine for the base size. We'll let this go down to 5% if it needs to. I'd like it to do better approximations of circles if it can. We only have one surface. Surface proximity doesn't matter. Turn down the growth rate to something small, 1.05. Do 10 prism layers. It's probably pretty good. Make this 50% of base. Oh, actually, no. We're going to make this 75% of base with a caveat here. We're going to make a couple of surfaces. First, for the far field, so all the outside faces. That is the field far away. We're going to tell it very definitively, do not use prism layers. And use a new target and minimum size. For the entire thing, we're going to limit the entire plane on which we are simulating. We're going to limit the maximum size, which is effectively target size. Actually, I'm not going to change minimum. I'm just going to change target. Biggest it will ever get is 400% of base. We're going to make a new surface control for the trailing edge of our wing. Just this little sliver here, because this is a relatively tight curvature. And it's probably going to give us some minor issues. We don't. Let's see here. We're going to change the target. We're going to go 25 and 1 0.25. We're going to let it get real small. We're also going to change up the prism layers. We're going to reduce the prism layer thickness. Even that might be too. Remember, this is a 2mm round, 2mm radius, and the prism layer is in this position 2.5mm thick. That might be a bit much, so we're going to reduce this to 18%. That's probably reasonable-ish. And then we are actually going to create two more controls. A little bit fancier. But we do want a wake new surface. Trailing edge, refine. Name. So we're just going to select the entire wing surface. And we're going to do a wake refine that just goes in the positive X direction. Wake refinement. Set some values here. We don't need to go 10 meters, I don't think. Well, maybe not quite 10. We'll go 8 meters. We'll do a 5-degree spread. An isotropic size of 150%, let's say. We'll turn down the growth rate to 1.1. But this airfoil is going to rotate, right? At some points, it's going to be at quite a high angle of attack. Airfoils at high angle of attack don't just have flow go backwards, they have flow go down. We'll very rapidly leave that cone. We're going to create a new wake control. I'm going to call this wake AOA. Get rid of the copy of up front. Shrink that, shrink that. Oh, it's just... Okay, that's fine. Wake control AOA. So the only difference we're going to do here is we want to change the direction that this is going in. So this should be 3 components. So we're going to do... This is going to be a trig function. This is going to be cosine of whatever that angle of attack is. And it's going to go down, so negative by sine of whatever that angle of attack is. So this should cause this to create kind of a cone that sweeps back mostly, but also down. Let's execute this mesh and see what it does. Might have overcooked this mesh slightly, we'll see. By overcooked, I mean it might have more cells than is reasonably appropriate for the simulation. Okay, so let's take a look here. New scenes, mesh scene. Oh yeah, I might have overdone that a bit. But if you look closely, you'll notice there's actually two different cones here. One cone that's pointed slightly down and one cone that's pointed mostly horizontal. But we do not need that many cells all the way out there. We're going to do a couple of things here. We're going to change up the far field target to 800. And we're going to limit the overall maximum size also to 800. And try that again. Because let's see, how many cells did it actually give me? I wasn't paying that much attention. Almost 750,000. That's definitely a bit much. Like 250,000 cells would be appropriate, or maybe even slightly overkill for this sort of simulation. There we go. That is much better. Okay. Take a look at the trailing edge. Now, we still have some issues here. Primarily... well, it's actually not that bad. My primary concern is in a couple of places here, this prism layer gets really thick. Or sorry, it goes from this outside cell is really narrow, but really thick. Could be an issue. Um... Uh... Layer thickness to surface size ratio. Okay, this is probably fine, actually, because this is an aspect ratio of about 1 right here, where it's about as wide as it is thick. This might approach an aspect ratio of 2. But I think by and large, that's probably still pretty close to. And then in most places, the boundary layer is quite reasonably sized. Okay. That's probably okay. I'd like to get it a little bit better where that trailing edge is, but with the geometry, I don't think it's going to be really feasible. Because you go from a smooth surface, very tight curvature, which is a problem. Okay, so there's a mesh. Let's see here. What else? That's probably actually it. Let's do. I hate how it defaults to that directory to save. So we want to do a couple things here. We want to do some reports here. So let's have it spit out what is the center of pressure on our wing. Specifically in the X direction. Right now it has no solution, so that's fine. It's X COP, or better yet, COP OP in the X direction. the y direction. I'm not going to bother with z because z doesn't exist for a two-dimensional simulation. We are going to look at the force. Lift. Force. Drag. We are going to look at the CL. We are going to look at the CD. We are going to look at the CM. And we are going to look at the moment about the leading. Note that this is moment about the leading edge. I'm going to actually append a moment, coefficient of moment about the leading. All of these are going to be measured on our airfoil, but they're going to be measured in slightly different ways. CD is going to be force in the x direction. CL is going to be force in the y direction. CM is going to be moment around z, but around negative z, because a positive moment is going to be nose up for our purposes. Okay. So do a couple things here. We're going to make a couple more parameters really fast. Density, so we can pre-compute that. And what else? There was another density I wanted to do just a second. Not another parameter. Reference length. This one's going to be a static value of 2 meters. That's fine. Density, we're going to compute like we did before. We have our reference pressure divided by 287, which is R, times our inlet temperature. Okay. This is going to be mass per volume density. Okay. Which is not quite 1.8. Not quite 1.18. We can go ahead and change up our velocity equation here, simplify it a little bit. So we are computing. We can get rid of everything inside of here, and we can say it's going to be our reference length times our density. I'm also going to change the word density to inlet density to avoid clobbering a keyword by accident. Computing that. Velocity. An issue here. Thinks there's. Oh, right. I was clobbering a keyword because notice how I changed it to reference density instead of density, but this state or inlet density. That means there's another keyword density floating around that it was trying to talk about instead. There we go. So a Reynolds number of 1e to the 6th. It thinks it has an inlet velocity of what? Oh, excuse me. It just crashed on me. That's unfortunate. Okay, well, let's see where it saved. I did save it at some point. Oh, that's unfortunate. And now we wait. Okay, where were we? Oh hey, I had created most of everything already. Perfect. Back to these parameters. Um, Interesting. I'd actually done almost all of it, thankfully. Take a look at this real fast. Let's density. I'm just going to delete this entire phrase real fast. Let density. Okay. Okay. Computing out at something. Fine. Dimensionless. Pressure, length, velocity, temperature. Is there just a value for density? I don't think. Nope. Okay. Pressure, time, Pascal seconds, angle, degrees. Yeah, that's fine. Because I'm a little bit paranoid now that it crashed, I'm going to save this as version 2. So, for all of our values here, we're going to set our reference density to our inlet density value. We're going to set our reference velocity value to our velocity. We're going to set our reference area to our reference length times 1. So as if this wing, or as if this airfoil, which we're simulating in 2 dimensions, exists 1 meter in the z direction. It has a 2 meter chord and 1 meter span. That means it has a reference area of 2 square meters. We're already measuring those appropriately. Lift and, oh, excuse me, drag is measured appropriately. Lift is not. We're going to measure lift in the actual correct direction, positive y. Moment about the leading edge, we're going to measure about the negative z-axis. Y is correct. And we're going to create some plots. But you can create multiple plots from the same thing by clicking multiples. I'm making most of these singletons because otherwise lift is reasonably expected to be much larger than lift is reasonably expected to be much larger than drag, both coefficient and force magnitude. So if we put them all on the same graph, then they have a very good chance of the lift will drown out the drag, and you're not going to be able to tell what the drag is very easily. We can create another plot, which is just going to be a combination. So I'm just going to call these force coefficients. And we can create another plot from our lift and our drag plot. We're just going to call this forces. Okay. Save. We should be okay. Oh, cannot evaluate. Oh, did I save just before I updated the thing? Wait, what? Okay. On simulation continuum, matter physics continuum, static temperature profile. Oh, right, because it's actually inlet temperature. Again, we accidentally used a keyword that the simulation software uses. So let's try that again. Perfect, initialized. If we go check our scene, did we make a scene? We did not make a scene. Let's make a new scene. New scalar scene for static pressure, let's say. We can see there are values everywhere. Have it iterate a little bit, just once. Yeah, it's figuring out what the velocity field looks like. Okay, so let me make this a more intuitive one. Instead of glyph, I really like the line integral convolution way of displaying vector fields. We'll see what this looks like. We're starting to form our stagnation point up front. Keep in mind, unless you have a fairly powerful consumer computer, this is probably not going to run this fast. It's 14 pretty fast cores. Take a look at our drag plot. Yeah, lift is still steadily increasing. Definitely not done yet. Moment is still changing. All of these forces coefficients are still doing things. We cannot stop it yet. Residuals are looking even TKE, which is normally a somewhat problematic one, is trending down nice. I'd like to see these get generally a little bit lower. Oh. Trending down, just kind of annoying. Really, this effect probably wants to propagate off the domain if we can Let it. Let's see here. Oh, yep, that was a little bit ambitious. I thought messing with those values could have broken things, and it did. That we're gonna turn these back down. Yeah, you see that? That would have crashed very rapidly. Oh, and it hit that default 1000 iteration stopping. We're gonna actually go to 4000. We're gonna let it go to 2000. Let it keep on going. Take a look at all of our plots here. PL seems to have pretty much flatlined. CD also flatlined. All of our properties seem to have pretty much reached steady state. That's good. Up that. I'm going to start it from scratch and see if it still runs. I did tweak some fairly important values. Theoretically, those should, if it doesn't crash, make it converge faster. But that's very dangerous to mess with because it can make it crash. This seems reasonably stable. We'll take a little bit of time to figure out these oscillations behind the airfoil. Let's take a look at all these values. Yeah, they're still. Oh, we're actually going to introduce a new parameter, by the way. New scalar base mesh size. We're going to do this because one of the things to determine if a simulation is truly giving you fairly accurate results is to modify the size of the mesh and see if the results change. We're going to just remember that our base size is 1 centimeter. And we're going to tell it to re-execute the mesh, even though technically it doesn't need updating. We're just going to let it do that. So it doesn't warn us about it. Takes like 30 seconds. We're just going to let this run for a little bit. And we should see these values spike a little bit on residuals and whatnot. Oh, I guess technically not, because it's pretty much the same. But I'm going to let this run for a couple of minutes, and I'll be right back. Okay, we're back. So, 1 second here. Yeah, that's better. So it ran out to 2,000 iterations quite clearly. That was not more than like 7 or 8 minutes. Pretty good pressure distribution, like I'd expect for an airfoil like this at this angle of attack. Let's see here, residuals. Again, ideally I'd like to see them lower, but for a relatively benign flow field where it honestly wasn't changing all that much from the initial conditions, like the inlet velocity is only like 15 an hour. That's probably fine. All the force coefficients pretty thoroughly flatlined. We can zoom way the hell in and see that they're oscillating about a pretty much fixed value. I'm actively trying to drag this up off the screen, and we can see that, yeah, they're pretty much staying. So we do indeed have a pretty solidly converged simulation. Our metrics aren't changing. Our residuals have pretty much not flatlined per se, but they've been pretty consistent for the last 1,000+ iterations. So we're going to save this for and I think we have our plots. We have a couple of scenes. Static pressure. This is going to be velocity. That should just about be it. So save this again. I'm going to start a new file. Instead of a simulation, we're going to start a design manager project. A couple of differences here. Big one is this is going to be this design manager project. And instead of, we're going to add a command -dm space after the last one -dm no share. See if this works. I know some of you have been having design manager license issues. We really probably won't be doing this too much in the future, so hopefully that won't be an issue. Hopefully that's not an issue right now. actually open. So we're going to tell it to reference simulation that we just had set up. Our POD license. Note that as of the posting, this key will need to change. So that key will be valid, but better. Let's see here. Parameter. Have all of our parameters. We're going to create actually 2 design studies. First of all is going to be a sweep with a couple of input parameters. We're going to change our angle of attack and our Reynolds number. So, going to be a resolution. No, we're going to do a discrete sweep here. So we're going to do 100. This is going to be. This is not going to be the exact same as you should be doing. Advised. 100,000. So 1 e to the 5. E to the 5. 5. 5. 1e6. 5e6. And e. And then we're also going to do a continuous sweep from, I'm going to do -4 to 24 degrees in 2-degree increments. Tell it to do 1 degree. Okay, so it's reconfigured. Perfect. And 2-degree increments. So that'll be a lot of data points, honestly. 90 data. Actually, no, we're going to do 23 instead. We're going to do 1.5 degree. So responses that we're looking for here are pretty much all of these, honestly. Want to monitor all of these things. We want to snapshot specifically our static pressure and our velocity, also our mesh. We want to take all of our plot. Be a pretty lightweight thing, so we're going to just basically grab all of it. I'm actually going to tell it to run 2 of these at once, both of them with 7 cores. Don't save the simulation files. Okay, that's what I thought. So compute resources, our default is just going to be pretty much whatever you use for our simulation. A couple of so I'm just going to attempt to open that, copy. We're going to get rid of the dash server. And I think that's probably fine. We'll find out. Einstein. $114 different designs. This is a bit more robust than I asked you to do. That's fine. By robust, I mean snapshot. 2 snap. REAOA. Snapshot. A pressure. Oh, well, actually, I don't think that matters. No, got it. So, a couple of from design study. Bottom axis is going to be a parameter, specifically angle of attack. The left axis is going to be CL. This is going to be CL versus AOA. You plot. Actually, I'm going to copy this one to make my life a little easier. Differences. This is B. I'm not going to plot all of these right now. We're just going to plot some of them. CL and CD being the big. I want to make actually a new design study. Going to be mesh independent study. Going to input our base size. And we're going to input our angle of attack. And we're going to do a couple of things. We're going to use 2 angles of attack. We're going to do a discrete. We're going to do 2 degrees, 12 degrees. And we're going to do a 3-point resolution switch. But we're going to do it slightly narrower. So 0.8 centimeters, 1.2 centimeters, and 1 centimeter. 1 centimeters in the middle started. 0.8 and 1.2 are on either side. And the response, again, we're interested in, well, pretty much everything, honestly. Monitors, again, we're interested in pretty much everything. Scenes, pretty much everything. Plots, also pretty much everything. This should just be run pretty much in the same way. 2 simultaneous jobs, 7 cores per job, save log files. Fine. That's it. Save this as manager are that. Let's see if this works. This is AOA RE. Okay. And save again. Output. Let's see here. This is not going to do anything. I know it's not going to do it. Um, because our reference simulation has a stop condition at 2000 iterations, and it was saved at 2000 iterations. It's going to take a second to finalize that. That is okay. Let's you know what? We're doing enough stuff here where we're changing enough things that I'm going to just save it. Save that. Just because initial conditions aren't really going to help doing such a wide range of velocities when there's a wide range of angles of attack. Might be appropriate to help some of the simulations. It's probably just going to hurt others. So let's try this again. I'm going to tell the study to run and wait. And I'm not going to necessarily make you wait with me. I'm going to pause the recording and we'll come back to this. Just to drop in real quick here. Still running the first two designs, but we can see that is running two of them at once. Also, there we go. Not make a secret. Anyways, whatever. These last 8 cores only have 2 threads apiece, but it's using every other main core because CPU 1 is actually a hyper thread of every other main core, of which there are 8. And then it's using 6, 3, 4, 5, 6 at pretty much 100%. Oh, hey, it just finished the first set. Working on finishing. Notice how all of these dropped. Or maybe it just finished. It finished something clearly because a lot of the we'll see exactly what. I think what happened is finishing one of the simulations. This one is running slower because it's using efficiency. Yep, one of them finished. Slight negative lift, which we expect at such a low angle of attack. It's got a nose down pitching moment. We expect that. We're measuring edge. It actually is a negative coefficient of lift. So the center of pressure is forward. That doesn't seem. Maybe I measured those backwards. Drag is positive, lift is negative, moment is negative. Let's see. It should. If I dig around in here. One, design manager assignment one. For design one, we should have. Oh, okay, hold up. I want to change something. It's saving these scenes as well seen. Don't want it to do that. I want it to save these as hard copy. I don't want to have to open the viewer to view these. I will open the viewer to view these, but let's see here. I want to look at the static pressure scene. RCC viewer. With okay, this RV. Okay, no, actually, I can kind of see why it said that because pressure is actually look at all of this pressure forces. Center of pressure would actually be out in front some. Is yeah, somewhat. That's out in front by. Might have to debug that a little. But in any case, this is actually running. This is actually running. It's running the next two. That took 10 minutes on this computer for two of them. You don't need to run this many. I think you have about 40 something further to run. In probably most cases. But it'll probably take you several hours. I'm probably not going to actually run all of these, at least not right now. But in any case, hopefully step through that really slowly and you remain having problems. This will help you. Very, very late. at this point, so you will probably not have it turned time if you're using this. But hopefully this will help some.